and all the valves that are like primary reactor boundaries and stuff like that. And obviously, I went inside. I've been inside the reactor room before, so like I've stood on top of it. It's pretty crazy to stand on top of a multi-billion-dollar nuclear reactor.
But yeah,
that was pretty cool.
Don't drop the wrench.
A little bit nerve-wracking.
It's really not actually. It's warm. Like even when the reactor shut down, it's still like 120 degrees in the space.
Daddy, can you please get me into my class?
So, but yeah, so I worked with like radiation components and all that stuff like that, and like controls and like working on certain valves. You have to like put all the PPE on and like take it apart and do those crazy stuff. So like, and we have to know like the amount of knowledge that they require us to learn for that is obscene. So it's like I did that. Then I got out of the service and like there's all these jobs for the nuclear field, and they're like, yeah, do this. And I'm like, but we make you take a test every single month to make sure your level of knowledge is advancing with current world trends and everything else. I'm like, I'm not trying to be a student at my job.
Yeah.
So I was
like,
just
do your job.
Yeah, I'm either trying to do my job or I'm just gonna be a student. I'm not trying to do both at the same time.
Yeah.
So here I am.
Morning, everyone.
Morning.
Greetings and welcome to your life on Thursday. Just kidding.
Is it Thursday already?
Yeah.
You guys are being taught calculus by somebody who doesn't even know what the day of the week is. I feel sorry for you.
All my days run together at this point, Doug, so you're safe.
Right. You don't know
My
what
wife asked
either.
My wife asked me what month it was the other day, and I said, I don't know. Is it still October? I was like, wait, no, we had Halloween. It's past that. Whoops.
Learn new things every day. So let's see. You see my screen now, and all this time I thought I had to have this iPad plugged into my computer, and I do not. Unplugged. It works. I don't understand these things.
Computers are like electricity, magical.
So what we are looking at now is, as I mentioned before, we're just looking at applications for derivatives. Unfortunately, they back off. Like the hardest applications for derivatives there are, you just got finished with. Related rates or the hardest application. You're gonna actually feel like today is a bit of a breath of fresh air. The project addressed this, and we're going to just build a little bit more foundation underneath the project a little bit. But it's kind of all about this concept, just to kind of put it quickly, simply introduce it. If I have a graph that looks something like this, for ancients, and by that I mean myself, given that when I took all of this stuff pre-calculus, there wasn't a graphing calculator. So if we wanted to graph some cubed equation or fourth degree equation like this, it was kind of really hard to graph it. You could find the ordered pairs to graph it, but does it make sense if you could find this point, and this point, and you already knew because it was a fourth degree equation, and maybe you know from your great memory of math 111 or pre-calculus that this is a fourth degree equation because it's pointing down, and then it's got 1, 2, 3, 4 changes of direction. That's kind of the way I think about it. That's the my for dummies way of thinking about it. So I already know a fourth degree equation is going to look something like this, and so if I already know it's kind of M shaped, and then thanks to calculus, if I could find these 3 points right here, these maximums and minimums, then I could graph this without suffering so much, if you will, without just finding random points. Does that concept make sense? And of course, you understand from the project yesterday, and we've been alluding to this a long time, that of course, what makes those
There's no flux
maximums and
anymore.
minimums
It's
what
just
they are
barely.
is a slope of 0. So
Oh, I thought you were in class already.
Andrew, you should probably mute.
I just muted Andrew. So in a sense, what I'm showing you today is partially archaic in the sense that we have graphing calculators now. So it's like we don't need calculus to find those points because we can just bust out Desmos, graph them, and say, look, there they are. But nonetheless, it's still a cool concept. And then secondly, it's not so much, just to graph this concept, but if, and I've alluded to this a little bit before, but if this was a model of, say, the stock market or something like that, being able to find a function that modeled it and then say, yeah, this is a good time. Like, I really need to know where that happens right there, because that's the time to sell, because it's at its highest value. And then it goes down to here, and now this is a time to buy. So I'm actually not trying to graph it. I don't want to graph. I want to just take the equation, take its derivative, and set the derivative, which again means just slope, set that equal to 0 and sort of find out where these places are. Because as you know from yesterday and earlier discussions, those places are all unique in the sense that they have 0 for their slope. So this section is really easy. Like, all you have to do is take a derivative of this statement, which we've been practicing, set it equal to 0, solve for x, and you found those points where the slope of your graph is 0. And of course, in your world, because you have Desmos, you can verify that. Like, you can check your work, if you will, and see that you're right, which is kind of cool. Now, just a little bit of terminology. Do you agree that those are kind of maximums and minimums? And yet, would you agree that what I was calling point number 2 is actually more maximum than point number 1? So there is a little bit of language here that I don't care about, but I don't want it to screw you up either. Number 1 is not called a maximum just because, well, in the language of everyday life, that isn't the maximum, right? Isn't 2 like a higher price for the stock? And so 1's not a maximum, yet it kind of is a maximum. So what would you call it? I mean, that's kind of the question I would ask you. What would you call it?
A local maximum.
Yeah, maybe local, because it's in that local region. During the years 2008 to 2010, that was the maximum or something like that. So that's a word that books use as local maximum. You also hear the word relative maximums, like in that relative to the points around it, it's a maximum. And so I prefer to keep it simple. Like, if I was teaching this stuff, I mean, I couldn't write it in a book. You can't write in a book, these are maximums and minimums, because it's not sort of technically precise. But I'm just going to be lazy and call them maximums and minimums and not even distinguish. But you'll be asked in a book for the names of these. And I do need you to understand that this is called a relative. I think the My Open Math homework calls this relative, but also local max. Whereas this point up here, point number 2, is called an absolute maximum. These are not questions I'm going to ask on a test. I could care less about the language of this, but I want you to be able to get your assignment questions right. And so if they ask for an absolute max, what if the graph was upside down, like it was let's say it was a cubed equation and looked like this? What would you call the absolute? What would you call the absolute maximum of that graph? It's kind of a trick question.
Would it be infinity?
Yeah, like notice how the arrow just kind of goes up forever. So again, it's, in a sense, it has a maximum here. And again, that's the only word I'm going to use. It has a maximum. You know what I mean by that? It's a maximum, but then it's not the absolute max, because the stock just goes up and up and up. Now, one of the things that the book does that I find just unnecessarily confusing is, what if you chopped, whoa, that is not what I wanted to do. What if you chopped the top of that off and you said, hey, this thing actually only exists between, and remember how interval notation works. Let's say X only exists between -3 and 7. Let's see. And maybe I'll put brackets just so you don't think that's an ordered pair. So, what if this graph, although it does go up forever, this person is saying, no, chopping it off at 7. Does it make sense? It actually has an absolute maximum now. it's kind of contrived because you're saying the graph gets chopped off, but now that would be the absolute, that'd be the absolute maximum. And this would still be, this point over here would still be kind of a relative maximum. And so anyway, there's a little bit of terminology that makes what I consider to be a super simple concept, and I want you to think it's simple too. It can make it a little bit weird. And so, okay, well, let's dive into this. And so of course, calculus basically then allows you to find these maximums and minimums, these low points and high points, which is why business calculus exists. You can see why somebody in business would want to understand if you had an equation that was somebody's profit margin or something and it was all complicated and awesome, why they'd want to be able to know what the maximum was, because you're trying to maximize your profits. And so anytime you hear the word maximum or minimum in the real world now, that's kind of code for, hey, slope is equal to 0 there, and that's a calculus concept. So let's just start off with kind of a good example. Let's see, how am I going to say this? I think I'll say it like this. Just looking at something I had written down in my notes here, so I'm assuming I spent some time with this, and it's kind of a good one. So here's this graph. You should already know something about it just because it's cubed from Math 111. You already should know a shape. And its leading coefficient is 1/6. So this is really 1/6. The shape of this thing is determined entirely by the 1/6 x cubed. So the two things you're looking at there is, hey, it's cubed. I know what those look like. And the second thing is, oh, it's 1/6. It's positive. That's the two things you're looking at. What does a positive cubed graph look like? Do you have a picture in your mind of what that might look like? Again, the answer to that is supposed to be yes, of course we do. We studied Math 111. You probably still do have this one. This is not one of the concepts you tend to lose as quickly as completing this.
It would look just like the graph you just wrote above it.
Yeah, it's like that blue graph I just wrote above it. So
Wouldn't it be pretty flattened out though? Because that 1/6.
Nice job. So the one
Kind of close to our chair.
being the low number, that's right. This is more like your chair. This is the chair you're working on. So it might be a little on the lower side, if you will. It might look something like this. And so in a sense, I would expect there to be a maximum here and a minimum here or something like that. Like I'm already looking for that. So the question is, can we go find those right now and actually make a pretty decent graph of this without even having a graphing calculator? Like if we locate those 2 points and we know the shape, does it make sense we pretty much have the graph? That's the idea. Does the 6 on the bottom bother you? Maybe a little bit. You got a couple choices. You could just multiply it over to the other side and have it be 6y. 6y equals all that, and then you want to have that dumb 6 down there. Or you could say, well, isn't this quotient rule? Or you could, I think this is the approach I'll take. You could take the 1/6 and kind of think of it as being out front multiplied by everything. And if it's out front like that, now it's more like product rule. And product rule would say derivative of 1/6, which is nothing, times the derivative or times the x cubed left alone, plus the 1/6 left alone times the derivative of the stuff in the parentheses, which means the 1/6 really just comes along for the ride. And so if I say f prime of x, I can know that the 1/6 comes along for the ride. And you look at that equation, you think, thank God, like the power rule. Good old days of power rule, the easiest one possible. So the derivative of that is 3x squared minus 6x minus 24. And of course the 12 goes away. And really what we're interested in this section collectively, because maximum and minimum is 2 words, your book annoyingly adds yet another piece of terminology to this and really just calls these critical points. Again, I would not even be saying these words to you because I feel like terminology is kind of a waste of time, but you're going to have book assignment questions that say, find the critical points of this. And, if you don't know the code, you don't know the secret code. But that's not a bad name. If I was to make up a name for this, that's a good name for it because those are critical. Like if you could only find 2 points and you had to graph this, equation, wouldn't these 2 be the best 2 you could possibly find? I only have to find 2 points and I could graph it. Those 2 points are critical. Points up here, like just random points up here or points down there, those aren't really that critical. They're not that important. They're not key players in what this graph looks like. So I get it. I mean, you know, I can track with that. I see why they're calling them that. That's actually not a terrible name. So how do we find those? Well, what are the critical points? The key concept to this is this: critical points, AKA maximums and minimums, are found by taking the derivative. What are you going to do with the derivative?
Factor it.
You're saying that for a reason. Like, why would you? What are you doing when you're what's the simple answer? Simpler than what you're saying.
Finding the zero.
Yeah, just set it equal to 0. And again, that's something you studied in Math 111. You know how to find zeros of things. So like this is the key thing. That's the key to, you know, what it means. And so, okay, well then what are we doing back in our orange graph? We're saying, okay, cool. When does 1/6 times 3x squared minus 6x minus 24 equal 0? And in this case, because it's a squared equation, maybe it's possible to solve that by factoring. Your knee-jerk reaction to that, I hope, is to say, oh, squared equations, quadratic formula, I have that in my calculator, and just let it do the work for you. But you know, what about the 1/6 and all that? Well, it's an equal, so can I multiply both sides by 6? Like if I'm gonna have to plug stuff into the quadratic formula, multiply both sides by 6, and the 6 makes no difference. And then I notice all of them divide by 3. So if I divide everything by 3, then I get this. So like that's easier to put in the quadratic formula. I will just do one quadratic formula example. Quadratic formula says x equals negative b plus or minus the square root of b squared, which is 4, minus 2 times a times, not minus 2, it's minus 4, isn't it? Isn't it minus 4? It's minus 4. Just kidding. Minus 4 times a times c, all divided by 2 times a. So I get 4 plus 32, which is, hey, 36, cool. I got 2 plus or minus the square root of 36. What that means is I'm going to get exact answers. Very seldom can you ever take the square root of something and get a whole numbered answer. You usually have to round that off. And it also tells me that I could have got this by factoring. And if you're sharp, you probably notice that. Like it's kind of a waste of time in this problem. Maybe you can easily see that x squared minus 2x minus 8 factors to x minus 4 and x minus 2. If you happen to notice that, that would save some time. But I just like stuff that's foolproof. You know, I'd rather just use the quadratic formula every time. So let's see, that's 2 plus 6, which is 8 divided by 2. So that's 4. And then 2 minus 6 is negative 4 divided by 2 is negative 2. But again, what did you just find? You found the x coordinates for the, remember those are x's. So I'll rewrite this, x equals 4 or negative 2. Maybe I'll just, this isn't the answer, but it's pretty darn important toward finding the answer. So when x is 4, there's a slope of 0. When x is negative 2, there's a slope of 0. This is like your Adirondack chair. Notice it came out nice whole numbers. That's kind of cool. Your Adirondack chair project is working backwards. You're trying to get a graph to hit a couple of points, whereas this is, in a sense, a more traditional kind of a question. So, okay, I'm really on the hunt as to what this graph looks like. So what do I need to know in order to graph this? Well, I also need to know what the y coordinates are. So I need to go back and figure out what's f. If I put 4 back into this original equation, and again, it's just cool to be able to do this by hand. I mean, I would tend to, if I'm you, I'm going to check this on my calculator anyway. So I'd probably be typing this into my calculator or Desmos, and I would type f of x equals 1/6, and I would just say, what's f of 4, and let it tell me. Do you see yourself as like that's a boring waste of time to you because you're really good at basic algebra? And also you make mistakes, and so it's a little dangerous to go put 4 back into this statement back here because I might screw it up. And so it's like, let's let technology do it. And I'm going to want to graph it and check it anyway. So, let's let technology do this for us. So I'm going to do that, I guess. I don't trust myself anyway. And since Desmos is one of my apps, why not just do that? So this is my advice for you on your homework. This is my advice for you on a test. And remember, this is why function notation, where you don't say y equals, you say f of x equals, is so cool, because then I can say later on, what's f of 4? And it'll just tell me, right? That's cool. Instead of having to, I don't have any other way to kind of type it in. So let's see, I guess I'll just type the 1/6 out front, and then I'll throw the parentheses in here. Doesn't this feel good? It's like finally something that's just not so complicated. So minus 24x plus 12. And I need to know what the y coordinate is for 4. So I say, cool, what's f of 4? But what might even be better than f of 4, because now I know the y coordinate, might be even to say, well, why not just graph the entire point for f of 4? I mean, while I'm at it, that's checking my work, because where do I expect this to be? Well, I expect it to be at one of those maximums and minimums. And so sure enough, you see how that checks my work? Sure enough, that point was, kind of right on the place that I wanted it to be. So f of 4 is, I'll just say approximately, I think it was negative 11 1/3. So it's kind of weird to not just write it perfectly. And then while I'm at it, let's get f of 2. And for a second, I'm just going to pretend, I did this the long way. Like I literally plugged 4 in, cubed 4, squared 4, multiplied 4 by 24, and so forth. But I don't want to be done with this question until I actually get it graphed. Wasn't it negative 2? It was negative 2. F of negative, that was negative.
I guess you have to do it longhand though if you want the exact answer.
Yeah,
This one
notice
you
it
can kinda
doesn't.
guess.
That's a very good point. Notice it, in this case, it comes out as a fraction, and maybe you're, if you will, sharp enough to notice, hey, that's 6 2/3, because Desmos is set up to round to 3 places. And as far as I can tell, you can't control that. So, if my open math wanted an exact answer to this, it's, especially if that was like 6, not 6 2/3, but what if it's 6 2/7? Does it make sense you wouldn't recognize the decimal? And so now you're forced to do it long ways and so forth.
Forced to use a calculator.
I could actually,
Life is tough.
I know life is hard. I like that, Logan. Good thinking.
I was gonna say you could just plug in that number and hit fraction on your calculator, and it'll tell you.
That's right, because you could say convert it to a fraction. That's exactly right.
Yeah,
And
but if you take 0.667, it tells you it's 667 over 1,000. It doesn't tell you 2/3.
Yeah, it's rounding it off, which is why that last number was a 7. So does it make sense, like in my dinosaur age, when I was learning this stuff, we didn't have a graphing calculator. If I'm armed with these 2 ordered pairs, these 2 critical points, it's like I own this graph now. I mean, all I have to do is say, cool. So if I go over, is this wrong? What's wrong? -2. Well, I should be trusting my math anyway, so let's just stick with it. So if I go over
I got the same
-2 and up 6, I'm like right about there. I'm not going to take the time to graph it accurately. And then if I go over 4 and down -11, I'm down here. And armed with the fact that I know that this graph basically looks like this, we said, I know it looks like an S that's kind of shaping up, then I kind of own the graph now. Now it's not going to be perfect if I'm just trying to sketch it. I don't really know exactly where it crosses over here. Like it crosses over here somewhere. So I just kind of have to say, well, I know it peaks there and comes down here somewhere and crosses. And so it, it looks, that would be a sketch of the graph. And if you wanted to do any better, you'd have to do what you did in Math 111. Like these would be interesting points to know too, wouldn't they? where the y coordinate is 0, not the slope is 0, but where f of x is equal to 0, that's finding the zeros. We aren't going to do that in this section. But I kind of own the graph, and it's because I found the 2 critical points. I found 2 important points, and thanks to calculus, I knew what those points were, and now I kind of own the graph. And so, of course, then I go into Desmos and just kind of double check, does this actually look right? Does this actually look like it's supposed to look? Oh, cool, it crosses where I said it was going to cross. Those really do look like 0 slopes. Yay for me. So that's kind of awesome. And also remember that you already know this with respect to Desmos, but if you really wanted to cheat, what would you be typing here?
F prime of X.
Yeah. Now it's not as helpful as it used to be because I'm telling you not what X is. I'm not saying find the slope. I'm saying like unless we took a derivative and set it equal to 0, we didn't know to try F prime of 4. Does that make sense? So we have F prime of X here. So I could check F prime of 4 and I would hope to get 0. But now that I see the graph, I don't need to do that because I can tell that I'm at the maximums and minimums.
If you wrote F prime of X equals 0, would that give you anything?
I doubt it. Let's try that. Everybody understand? That's a great question, I think. Let's try. Like, will it somehow, answer that for me if I say F prime of X? My guess is it won't, only because, oh, that's kind of interesting. Notice what it did. I'm actually kind of surprised by that.
That's really
Oh,
neat.
it pretty much does work, right?
Isn't that cool? It kind of does work.
Oh, sure.
I was thinking it wouldn't work because computers aren't very good at solving equations, but it,
Well, you could also put F prime of A and then make a slider for A, and then you could get your slope at any point.
yeah, that's a good observation. So if I say F prime of, and this is what I'm talking about here is just kind of cheating. That's interesting. It didn't ask me for a number for A. I wonder if I can just tell it to put one in.
Because you have it set to equal 0.
Right, it's because I have it set to equal 0. You're exactly right. So do you see how right now the slope is -4? Does it make sense I could just drag it around and notice the trend? See how it's going -4.3, -4.4. Oh, it's going the wrong direction. I'll go back the other way. Oh, look, it's on its way to 0. This is very exciting. It's on its way to 0. It's on its way to 0. Ooh, ooh, ooh. Yeah. Oh, yeah. Look. Oh, 4. I mean, I'm cheating to. I mean, isn't it what an amazing world we live in that we have the technology to kind of play around with this in this way. But that's cool. But again, there's no, if you're in Desmos, there's no reason to do any of this cheating anyway, because you just like all of this stuff was a complete waste of time because I just go into Desmos. If I go into Desmos and graph it, I don't need calculus to, there's the maximum minimum. I'm just staring at them, go write them down. So do you see why I'm saying this is in a sense a little bit archaic? We have technology that does better, but it's certainly cool. And obviously, as I said, the real point here is not just to make a graph of some irrelevant equation like I made up. It's about, you know, what year should you sell your stock? Like you don't have a reason to graph that. You can do the problem entirely without graphing. That's kind of the idea. So I'm just going to quickly screen capture this and throw it into the notes if I can remember how. Oh, I did remember how. Amazing. But here's another thing that you'll be asked. And so, which also, again, I think could be construed as a little bit unusual. So this is -2. I'm just going to call it 6.7 just so that that's a little bit smaller. And this was 4, -11.3. Does this make sense to you? Since this graph goes on in both directions, does it make sense that right in here, the graph is increasing. And in my opinion, the answer to that should not be obviously yes, because if you think of this as like a ski run, it depends what direction you're hiking. If I'm hiking to the right, it's increasing, but if I'm hiking to the left, it's decreasing. But remember, a lot of times these things are pertaining to time, and because time flows linearly to the right, you're sort of moving to the right. And so mathematicians call this increasing just because you're working your way to the right. And then of course, over here, from here to here, wouldn't it also be increasing? And then, the graph doesn't end, so I should be putting arrowheads on the end of this. So during that time, the stock value is going up, 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 up. And of course, in here, the stock value is going down, 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 down. So that's decreasing. And notice where the transition is between decreasing and increasing is totally defined by these two maximums and minimums in this problem. And so you'll be asked some questions like that too. And I think you can see, although it might be weird to write it down, at least it's kind of important to understand, yeah, the stock is going up, we're up in this range, the stock is going down, it's decreasing, and then this range is going back up again. You can see why somebody in business would want to know that. But do you remember interval notation? You already did this in Math 111, but let's just remind ourselves. So, where is this increasing? How do you say that in the simplest way possible, because we're lazy mathematicians? It's increasing. Well, you list this by just x's only. So you say it's increasing. Well, let's see, isn't it increasing forever in that direction? So that would be negative infinity. And then it's increasing all the way up to right there, which we figured out was at -2. Do I say parenthesis or bracket here, do you think? If it's a math book question and we're going to get dinged for that technicality, which one do you think it is?
A parenthesis. Because
Anybody
it never,
agree or disagree with that? Justin thinks it's a parenthesis.
I agree with that.
and that's
I
because
agree.
it never really truly touches that, correct? Because it's a limit.
Yeah, when it touches that, it's flat. It's not going up or down. It's level right there. So that's exactly right. Technically, and as far as my open math is concerned, you better put a parenthesis there because it's going to say you're wrong. But again, that's splitting hairs, right? Like, who cares? In the real world, to be the guy that says, actually, it isn't increasing at -2, it's increasing at -2.0001, like, don't be that guy. Don't miss the point. But then isn't it also, so it's basically increasing during these times, that's increasing. But then here at 4, isn't it also increasing from here forever too? So again, just look at it as boundaries. Oops, that's not an 8. Look at it as boundaries. It's increasing from -infinity to -2, and it's increasing from 4 to +infinity. So there's the other. I don't know if it's going to make you put positive in front of that. Notice it doesn't actually matter what you put after infinity, because infinity is not really a number. I think classically people put parentheses for that. But I don't know if my open math would mark you wrong if you put a bracket there. Again,
I think
here. What do you think, April?
I think it will mark you wrong if you put a bracket.
Doesn't surprise me.
It definitely will.
Doesn't surprise me because it's a computer, it can't think, so I understand that.
I think you also have to put the union symbol, and it'll like turn that into a U. And then I forget what the other symbol was, but
Yeah, I was going to point that out, but actually didn't know if that was in your homework or not. Technically you put a union here. Again, this is all language and annoys me because it makes a simple concept complicated, but you're basically saying, you're joining them together. The word "and" is what union means anyway. So if you say "and," then good for you. On a test, I'm going to care less what you say there. But you might be asked in a textbook or in it where a computer is grading you, you might be asked to put the symbol union in front of it instead, because there's 2 different places it's increasing. And then of course it's decreasing. It's decreasing from -2 up to 4. Do you think this should be wrong? Is that wrong? What's wrong about that?
It's not flowing linearly to the right.
Yeah, it's just kind of bad language. It's kind of like saying to the store I am going, which maybe they do in Spanish. You know, say it in the order that people are used to hearing it in. It's like if you say to the store I'm going, people, okay, I guess you're going to the store, but that's weird. Again, I don't know if this particular program is going to mark you wrong for that, but again, we're moving from left to right. That's what defines all this anyway. You have to be moving to left to right. Otherwise, increasing and decreasing don't make any sense. So that's kind of cool. So you did the increasing decreasing thing in Math 111. It's just you had to be given the graph. The graph was already given to you. And now it doesn't need to be given to you. You can kind of do the math. By the way, just as a side note, if it's increasing, what's its slope? In other words, over here, what kind of slopes do you get if you evaluated it over here? Evaluated at -2, we get a slope of 0, but what kind of slopes are you going to get over here?
Positive.
Positive. So you wouldn't even have to graph this to be able to figure it out. If you knew what the critical points were, you knew that it kind of went from -infinity up to 2. I shouldn't use a dash probably for that. If you knew that it went infinity up to -2, and then it went up to +4, and then it went off to positive infinity, you would know that kind of means there's 1, 2, 3 sections to this. And if you took this derivative and evaluated it somewhere between here and you got a positive, then you would know it's increasing. Like you don't even have to graph this, which is kind of cool. It's kind of cool. Again, I don't know as I'm doing this without graphing it. I got technology. I want to check myself. And then if you picked any number between -2 and 4 and you plugged it in, and in that situation, I just learned something new. I got an arrow. Then you'd get a negative, right? Decreasing would be when f prime of x is actually equal to some negative number. So the slope is negative. Oh, that section's decreasing. I mean, isn't that kind of cool that you could figure all this stuff out without, you know, ever having a graph? And again, please don't let it be lost on you that people have understood this for hundreds of years. And it's only been the last 40 that people actually had a graphing calculator to get a good graph of this thing. So for hundreds of years, that was the only option. So that's kind of interesting. So in a sense, I think modern textbooks kind of overemphasize this now that we don't really need to be this good at these things, but it's kind of cool. I mean, it's kind of cool, I think, to be able to reason that out. All right, all I want to do now, like there's nothing else you need to know. You just kind of need to get this to sink in a little bit. So can you do the same thing? Well, just for some other kind of equations. So let's make up another example that maybe is a little bit more challenging. What about this? I have some examples written down from some previous time I taught this. I wonder if they're any good. When you stare at that, you might not have as good of a feel of what this graph looks like. Maybe in Math 111 you did, and maybe now you've kind of lost it. But does it make sense that you can, the first thing you always want to do no matter what is go find these critical points, like places where the slope is equal to 0. But this time you probably don't know what this looks like. And so are you going to get 1 or 2 or none? Like you could get no critical points. Wouldn't a graph that looks like this have no critical points? There's no places that have a slope of 0 there. It's not impossible to have none. But don't graph it, just do the calculus. Now, what are you thinking if you say critical points, which of course is code for f prime of x is equal to 0? What do you look when you look at that equation? What are you thinking?
Thinking,
How do you take that derivative? I'm not sure if I heard it.
I mean, you can do the quotient rule.
Chain rule?
Certainly
Thinking.
quotient rule, because you have junk divided by junk. Now from the test, could you avoid that and multiply both sides by x squared plus 2x plus 6? So you have y times x squared plus 2x plus 6 equals x minus 2. Can you get the derivative in a kind of a creative way? Absolutely. I'll probably just do it using quotient rule, even though I hate that one. But, you know, you know how to take this derivative now. So we bored ourselves to death taking derivatives of everything. And, you know, now in this section, we might need to be taking the derivatives of some weird things. And so I'm just going to give you a second to, and in a sense, I have to be just a little bit careful because, you know, this is meant to be kind of a calculus and algebraic section. Like I would want to see your work as though there was no such thing as a graphing calculator here, even though I expect you to check it. Take the derivative, set it equal to 0. I got to make sure the equation is solvable algebraically. There's, you know, I can make up one that's really hard. And so I did that here. This one's solvable algebraically. Are you ahead of me? What am I doing wrong here? I'm doing a classic idiot mistake that is really easy to make.
You're supposed to FOIL the second part, right?
Yep, which I did.
Just distribute the negative.
Yeah. Isn't this negative here? And again, I'm just reminding you of kind of common mistakes people make. That negative applies to everything. And so I did FOIL x minus 2 times 2x plus 2, and I correctly got 2x squared minus 2x minus 4, at least I think. But it's minus all that stuff. And, you know, that's the kind of thing you could screw up algebraically that's going to make it not agree with your graph. And then you're going to be confused. And so x squared minus 2x squared is minus x squared. 2x minus a minus 2x is 4x. And 6 minus a minus 4 is actually 10. So this is kind of a terrifying equation, but why is this actually not too bad? What is it I'm doing with this derivative this time?
Oh, you're finding the zeros of it.
Yeah, I'm setting this thing equal to 0, which means I can multiply both sides by that denominator. Like what makes a fraction 0? If you have a over b and it's equal to 0, does it make sense b could be 11, 15, 82, 97, negative 15? Who cares what b is? It's the top that's got to be 0. 0 ninths, 0 50 seconds. Like the top is what makes it 0, not the bottom. And of course, you could just do algebra, multiply both sides by b, and you get a is equal to 0. Like a has got to be 0. So in my case, although this is an ugly looking equation, if I multiply both sides by that nasty denominator, I really just have negative x squared plus 4x minus 10 plus 10 equals 0. Again, I'm thinking I haven't screwed this up, but remember, I could have made algebra mistakes or just accidental arithmetic mistakes. So I'm going to be checking this with a graph later on just to make sure I didn't blow it.
I think I did something wrong, but I got a nice answer. So.
Is it different than mine? Again, I kind of hope I did something wrong just because I need to model how to catch that. So if you got nice answers, I bet yours is right.
Minus 2x plus 1 equals 0.
notice in this form, I kind of like, I can't, if this comes out nice, I can't, I don't know about you, but I can't factor very good with a negative x squared. So couldn't I multiply both sides by -1? 0 times -1 is still 0. And now maybe I can factor it. And I see now that I can't. So maybe this problem isn't nice, or maybe I screwed up someplace earlier and, you know, lost a negative sign or multiplied wrong, or, you know, any of 100 things I could have done wrong. If you see something I did wrong because yours is different than mine, then point it out and let's fix it right now. But I compliment how many of you on the last test. I mean, there were so many of you on the last test that checked your stuff in Desmos. I saw so many notes this time that were like, yeah, I checked it in Desmos and you already knew it was right. Or I saw notes that were like, I checked it in Desmos and something's wrong, you know, and I don't know what it is. And I gave people more points for that. Good for you. So I'm not satisfied I'm doing this right now. I make a lot of mistakes based on going too quickly because I understand this stuff. I do know what I'm doing, and I try to do too much stuff in my head a lot. So anything wrong with this? Anybody sees? So I guess I'm gonna have to use the quadratic formula. Negative b, x is negative b plus or minus the square root of b squared minus 4 times 1 times c all divided by 2 times a. So that's 16 plus 40, 56. Yeah, 4 plus 56 over 2. If you're good with square roots, perhaps you could simplify that, but this isn't a very satisfying answer because apparently I'm just getting decimals. As I said, I have no problem on a test, and I would prefer on a test if you don't waste your time with the quadratic formula. If you have a program in your calculator that just plugs this in. And so I'm going to cheat and do that now. Because what I really want to check my work is decimal answers anyway. And on a test, I'm not going to ask for exact answers. You're more than welcome to report exact answers, but you don't need to. So notice there's 2 x values here. Maybe you're good at simplifying. 56 is equal to 14 times 4, which means I could square root 4 and get a 2 out in front. And then the 2 divided out of 4 and the 2 divided out of the 2 that's in front of the square root of 14. That's a much nicer answer. Do you see that they would simplify to that if I had some nerdy reason to do that? But again, I'm just going to stick it in the quadratic formula. I put in 1 and -4 and -10. So I got approximately 5.7 and -1.7. So x is approximately, I'll not wimp out so much. I'll say 5.74 and -1.74. So there's the 2 x's.
I think you're right. I don't know what I did wrong, but I got a nice answer, so I'm not mad about it.
Yeah. Well, and you know, the tale's going to be told when we graph this in a second and kind of see if we learn something. And so notice this tells us we have 2 critical points. In other words, 2 places on this graph where the slope is 0. And I've taught math for 25 years. I don't really have a good feel for what this graph looks like. I have to think about it a little bit. I could probably say, oh yeah, I guess that does make sense. But this is kind of a weird graph. And so it has 2 places where the slope is 0. That's interesting. And so, you know, if I go back now and say, okay, what's f of 5.74? In other words, I'm getting the y coordinate for that point, and now I also need the y coordinate for -1.74. And I'm going to do this the blue collar way this time and just plug it in. I'm going to type the whole thing so that I can switch it out. So I'm going to type parenthesis x minus 2, 5.74 minus 2, close the parenthesis, divided by, open the parenthesis, x squared, so 5.74 squared, plus 2x plus 6 plus 2 times 5.74 plus 6, close parenthesis. If I didn't type that wrong, I got 0.07 approximately for this.
I have a question.
Yeah, go ahead.
Would it be easier to just put like 2 plus the square root of 14 in your parentheses? That way, when you go to do the other side, you just have to change the minus.
Now that's actually a really good point. Does everybody understand what Andrew said? Like now I'm going to go back and retype this whole thing. So he's saying if I had typed 2 plus the square root of 14, number one, it's perfect. But then when I go get the second one, all I have to do is change the minus sign. I have a lot more stuff to change. So I think that's an excellent suggestion. And I got to put a negative. And you may remember that your calculator, if you type -7 squared, even though -7 squared you think is 49, it's not. The calculator is going to say that's -49. So you got to be careful with negatives. So I'm inserting a negative.
Yeah, if you're putting a negative squared in your calculator, it's a really good idea to put a parenthesis around the negative number and then square that parenthesis.
That is exactly right. Or just put a positive because you already know it's negative. Like I have 5.74 squared. I'm just going to type 1.74 because I already know the negative is going to be positive. So again, I'm supremely not confident that this is the case, but for this one, I got -0.67. So what I think then I have for critical points is 5.74 and 0.07 and -1.74 and -0.67. That's what I think. And so, okay, if I go for a graph, if I go make kind of a rough graph, I think, okay, so then there's one of them right there. And -1.74, -0.67 is like right over there. That's kind of cool that I know that, but does it make sense? I still don't know. Is this look like that or does it look like this? Does that make sense? I don't know that yet. And the same is true for this point over here. I don't really know that yet. I don't really kind of understand what that might look like. So let's go check our work. Parentheses x minus 2. And as I said before, if I didn't have a calculator, I'm just in a sense getting lazy right now. Does it make sense I could pick other points around there and plug other x's in to see what the slopes were and kind of get a sense of, everybody understand that? I'm not going to do it, but does it make sense if I plugged in, well, here's 5. If I plugged in 5 and I got a negative slope, then I would know that this is actually a minimum. Does that make sense? If I plugged in 5 and I got a positive slope, then I would know that that point's actually a maximum. So I got some tools. I mean, I can do this without a calculator. That's just kind of neat to think about. That didn't work good. I was hoping it would move that whole thing down there for me and I wouldn't have to retype all this. Plus 2x plus 2, but that's not that big a deal.
Always just cut and paste.
Yeah, and on the app I'm having, I can't copy stuff
Oh,
with
yeah.
this, but on your
on
computer
iPad.
version, you got a keyboard, and so I still have the labels turned on. Those labels don't apply, so in a sense, nothing. All I have now is a graph, and so the question is it behaving like I think it should behave? One thing that's really cool about Desmos, and I don't think it does it with this calculator, but it kind of knows. Like, have you noticed in Desmos, if you trace along that, it actually kind of knows you might want that point down there. So in my app, I don't have that ability to do that, but you can trace along the graph yourself. But notice we said, what did we say that order pair was? -1 point, I forgot. Does that fit? Yeah, it does. -1.57. That's like -1.5. And then the y coordinate was -0.67. That actually fits. It looks like I didn't screw that up. And so that does look like a minimum. Notice over here, is there a maximum over here? Doesn't look like it, does there? But if you look close, is there a maximum there?
I mean, yeah, because the line is going back towards 0 when you get out towards 14.
Yeah, can you see it's getting back towards the axis at 14 and it's touching it too? What if you decided you wanted to see this a little better? What do you do?
Could type f prime of x equals 0. It'll give you a vertical line that shows you exactly where it is.
Yeah, as if, for instance, didn't we say that this point was 5.74? So isn't that the point that we think is a maximum out there? So I don't know about you, but that's not very satisfying. It actually kind of looks like it's right. But what you can do is go up there to that wrench at the top and notice if we wanted to really blow this up here, if we just made the X max to be the Y max to be 0.5 and the Y minimum to be negative 0.5, that's going to blow up this graph. So my Y max negative 0.5, I want to see a little bit of that axis, and the Y max positive 0.5. Do you see how now I can see it a little better? And I can actually see now that I actually didn't make any mistakes, which again, for me, I'm always like, wow, I didn't make any mistakes. I can't believe it. That really does look like a maximum. That's pretty cool. And maybe this is a better window for the rest of the graph now. So notice I had to distort it. And that's one of the cool things about this, because if you had graphed this, you probably would not have known that maximum was there. Now that maximum I have graphed, is that a relative or an absolute maximum?
Absolute.
Let's see. Yeah, it looks like the graph never goes any higher than that. So that's not just a relative maximum, it's an absolute maximum. And would you agree that minimum is also an absolute minimum? And so that's kind of cool.
All right, so my question is, this graph looks like it's kind of approaching x equals 0, but doesn't actually ever reach it. Is that one
Yeah.
of those?
You mean Y equals 0? Yeah.
Yeah, that's what I meant.
Yep. And that's a topic for limits too. Like, when you get way out there at 10,000, does this graph behave like you think it's supposed to behave? And so in a sense, now I'm happy, right? Because I didn't screw this up. So it turned out that had I picked any number between x is negative 1.74 and 5.74, I would have got a positive slope, because isn't it increasing between the green and the blue? Whereas it's decreasing in the other two places. It's decreasing from negative infinity up to negative 1.74. So that's kind of cool. Do you see how it allows you to kind of understand the behavior of the graph a little bit? And so if I had gone back and found a derivative on the left side of this in the middle of the 2 points, and on the other side, I would have got positives and negatives. And then I would have known something. I would have known, hey, I think this is on its way down to this point. Notice that the algebra says we're guaranteed that red graph out to the right does not turn around and come back up. Why can it not turn around and go back up way out there somewhere? Well, if it did turn around, wouldn't that mean there's another minimum out there? Like where it turned around and came back up, there'd be another minimum, and the algebra said there's not. There's only two. So it can't. It actually has to level out forever. And the same is true on the other side. So that's just kind of cool. It's kind of interesting. In a sense, what this does for, again, this is sort of nerdy, but it allows you to find hidden behavior in a graph. You couldn't tell. And that was true in this graph. You couldn't tell until you did the algebra, if you will, or did the calculus. And so it's just kind of neat, I think.
Zoom out far enough on that graph and it'll look like a straight line.
Yeah, exactly. Which is kind of why the Earth looks smooth from space, but it's like you get a little closer and it's really not. So let me just throw this photo in here real quick, since that might help your thinking. I don't think I'll take the time to trim it down this time like I should, but at least it's in there for you to kind of check your work. The only other thing that little worries me a little bit in the assignment is, again, there's kind of a hair splitting. So let's take this point, 5.74.07. It's, again, this is a super simple concept. Like you would say, oh, cool, that's a max or a relative max or an absolute max. It's a max. This was a max. The entire point is a max. Yeah, clearly. But some of the questions in your assignment will ask, what is the maximum? And if this was time and this was money, then the max might only be that for an answer. Does that make sense? Like, what's your maximum profit? Is the answer to the question the entire ordered pair, or is it just the y coordinate? Because that's the thing you're maximizing. When you say that's the top of something, isn't that the highest y value possible? So some of the questions will be asking for only the y coordinate, not for the entire ordered pair. Does that make sense? Which again is just annoying to me. Like, you might get it wrong because of that technicality when it's, you know, based on the graph. It's kind of like, well, that's the max. What am I doing wrong? So you have some questions that'll, like, instead of just saying, tell me the ordered pair of the maximum, which to me sounds like common sense, they'll have one space for this answer, kind of like, where is the maximum? And then what is the maximum? So you won't be writing it as an ordered pair. You'll be writing it as like, here's a box for 5.74, and now here's a box for 0.07. Again, so there's sort of dumb things that might confuse you in the assignment just based on how it's worded. So this is kind of cool in the sense that this was, I guess you might say, kind of hidden behavior that calculus uncovered. And that's actually kind of a fun part of this. If somebody goes to some trouble to make up a really kind of a crazy graph, you have to work really hard to create a graph that's got hidden behavior that even Desmos doesn't see, if you will, because you can never get zoomed correctly. If you zoom out far enough to see everything, then you lose that undulation that's in it and so forth. And so, you know, it's actually calculus that tells you to go looking for a point. And that's kind of what happened here, which is kind of cool in a simple way. You tell me about this one. One more example, and then we'll probably run out of time. Let's skip down here. I'll just say y equals. This looks like a book question. I say that because I see square root of 3 in it. So this is making me think. I can't remember where I got this problem. Except for, we're going to limit this and only look at it from 0 to pi. Why would you do that with a sine equation? Why would somebody say, let's only look at it from 0 to pi? And by the way, that's x is 0 to pi. Why would you do that if you were looking for critical points with a sine equation?
Because you would only want to see what's in the first two quadrants. I don't know. I'm not sure.
So you get one answer instead of infinity.
Yeah,
I forget how they say it, like plus 2 pi x or whatever.
yeah. Like, isn't there a billion of them? There's a billion maximums and minimums. And so with sine and cosine, a lot of times books will say, hey, you know what? Let's just look at one chunk of it so you don't have to write all the idiotic answers down. And so, you know, good for them. I think they're right. Again, see if you can do this. So notice this has got sine in it, but it's also got a line, the square root of 3x. So why this is like a sine wave plus a line or minus a line. So maybe we don't know what this looks like, but again, don't graph it first, just take its derivative and set it equal to 0.
Is that the square root of 3x or the square root of 3 times x?
X is not in the square root.
Okay, thank you.
Good question. And it would probably be good form if I had parentheses around the 2x, although you probably knew what I meant by that. It's kind of related to April's other statement. Sine of 2 times x is a very different statement than sine of 2x. Little classic chain rule problem.
Would the derivative of negative square root of 3 times x be just the square root of 3?
That's right, just like the derivative of 5x is 5. So the derivative of sine of junk is cosine of junk times the derivative of the junk, chain rule, minus the square root of 3 times x is just the square root of 3. So the idea in this section is hopefully you've practiced derivatives enough that you're not having to concentrate on that. However, that's really good practice because you'll still be taking some derivatives wrong. I mean, you've just learned how to do that. So you're going to make some mistakes in derivative taking, screw up the product rule, screw up the chain rule, that kind of thing. You'll make some of those kinds of mistakes. So let's see, of course, I'm interested in when this is equal to 0. So then I would say, all right, I'm gonna add square root of 3 to both sides and then divide by that 2. Oh yeah, this is a canned book problem, I'm now thinking, because that's a really cosine of x, not cosine of x, cosine of 2x. That's equal to something very, that should kind of jump out at you, is it? This is a canned book problem because that's not equal to 7 or something like that. It's equal to the square root of 3 over 2. That should jump out to you as, oh, this has an exact answer on the unit circle.
Yeah.
So I'm flipping to my trig sheet. Where am I looking on this trig sheet right now?
That's 60 degrees.
I'm looking for cosine, which is x. I'm looking for an x coordinate that is positive square root of 3 over 2. You said 60 degrees. There's another one. Where's the other one?
30 degrees.
Not 30. That's the x. That's the. I'm sorry. Yeah, it's not 60 because that's the y coordinate. It's 30
Yeah.
degrees. We're looking for an x coordinate, so it's 30 degrees. Where's the other one?
I remember in my mind if I knew it was one of those two had a square root of 3 over 2.
330 is the other one.
Yeah, 330 is the other one. And of course, because this is calculus, the answer to that is going to be not the degree answer. So that means 2x is equal to 30 degrees, but it's going to be the pi answer to that. Or 2x can also be equal to 330, which is actually 11 pi over 6. So then I finish by dividing by 2. And so x is equal to pi over 12. So there's a place where the slope is 0. And 11 pi over 12 is another place.
Oh, I threw out the second answer before I divided it by 2. I was like, oh yeah, the other one's way past the pi on the unit circle, but
Right.
yeah, gotta finish out the equation first.
So there is the x description for the maximum and minimum. And again, I don't know which one these are. This could be 2 maximums. Could it be 2 maximums and no minimums, or does it have to be one and then, you know, another? Does it have to be one of each, or can you have 2 maximums? Can you have 2 maximums and no minimums? My gut answer is no.
I don't
If you
think
have
so.
a maximum, don't you have to turn back around to have another maximum, which causes you to have a minimum? Actually, I've never thought about that before, but sort of feels like you have to have one of each, but I don't know.
Don't you have a flat spot in between them? Like you come up and have a little bump.
Yeah, but it's
Yeah,
still going
levels
to have,
out and then-
it's still going to have to level out, isn't it? Even though it's
true.
microscopic. I don't know. I got to think about that. Okay, great. I found the 2x coordinates. So now I want to go back and see what y of, because I'm trying to find the y coordinate now. I want to see what y of pi over 12 is. So I take the sine of, notice it's sine of 2 times y over 12, which is, let's treat this like it's a book problem, like we have to get it exactly right. So since I'm multiplying sine of 2 times that answer, that actually becomes pi over 6, right? Which actually means I can look it up on my sheet. And then it's minus the square root of 3 times pi over 12. So the sine of pi over 6 is the y coordinate of pi over 6, which is a half. So that's a half. and then minus the square root of 3 pi over 12. I mean, maybe I can find a common denominator and write it as one fraction, but wow, that's a, you know, an unfortunate answer. So one of my critical points is pi over 12. Maybe I will write it as one fraction. That'd be 6 minus the square root of 3 pi over 12. Again, I should be capable of getting exact answers. The reason I don't like exact answers, even though that's a really non-math teacher thing to say, is because if I graph this in Desmos, I'm not going to get pi kinds of answers, and I'm not even going to know if it's right. You see what I mean? And let's see, what's the other one? There's the first one. What's the second one? Well, if I go back and put 11 pi over 12 in there, let's see, I'm sine of double that, which is 22 pi over 12, which is actually 11 pi over 6 again. That's good. Minus the square root of 3 times 11 pi over 12. So that's the sine of 11 pi over 6. The sine of 11 pi over 6 is square root of 3 over 2. So this is the square root of 3 over 2. And really nothing changes with that other one except for maybe just ugly. Man, it's ugly. Maybe it looks better to put the 11 instead of the square root of 3. 11 first, 11 square root of 3 pi all over 12. So I guess I could say 11 pi over 12 for the x coordinate. And the y coordinate, if I find a common denominator again, I guess it'd be multiplying top and bottom by 6. So certainly could factor the square root of 3 out of both of those, but I don't know what good that would do. So really ugly answers.
Cosine or the sine?
Sorry?
That was-
Isn't the sine negative 1/2?
yeah.
Yeah, I wrote down the cosine. I'm an idiot. Again, how am I going to catch that? So remember, sine is the y coordinate. I looked at 11 pi over 6 and I wrote down the x coordinate. So I made a mistake, a dumb mistake, not an important mistake, a dumb mistake. But then I'm going to go to the graph in a minute and check it. And then I'm going to go, hey, one of mine's wrong. Why? You know, and eventually a half hour later, I'm going to solve it, right? So let's just quickly go back and fix that. This is supposed to be negative 1/2. Thank you for catching that. So I end up with negative 6. So if I multiply the bottom of that by 6, top and bottom by 6, I get negative 6. Is that fixed? Did I get that right? I think so.
Unknown caller.
Goodbye, unknown caller. So again, I'm in the same place I was a minute ago, which is, man, I wonder if these are right, or I wonder what this looks like. It has 2 critical points again in that window. So in the interest of time, I kind of would like to take a derivative somewhere else and kind of determine, you know, is this, but it's kind of like last time. Like I have these couple of points here and, you know, again, they're really strange, but I want to look at the graph. And it's like, this is no fun unless I actually check to see if this really told me what sine looks like. And I'll show you another kind of a cool trick here. So if I say the sine of 2x minus the square root of 3 square root of 3, and I got to hit an arrow to get to the right x. Now remember, my window's all jacked up from the last problem. But here's something kind of cool. Remember, we're only looking at this from 0 to pi. So I don't know if I've ever showed you this before, but now that the equation's done, you can actually limit its domain so that you don't have to see everything. So before I fix the window, which I'll do in a second as well, I'm going to go in here and add one more thing to this if I can find out where these things are. If you put these brackets in down here, if you say bracket, and then you just list it in common sense language. Thank you, Desmos, by saying 0 is less than or equal to x, which is less than or equal to pi. And then you go back and close that parenthesis off. Notice And again, notice I have a weird graph right now. So let's go back to notice there's a thing here called zoom square. You can fix, instead of just doing it manually, I can kind of fix that, at least to get a start on this, to what this might look like. Come on, there we go. So, oh, look, good. Doesn't it look like it has one maximum minimum? I don't know if the ones I got are right, but let's at least check one of them. So, since we have a second, pi divided by, was it 12? Yeah, 12. Oh, good. I got it right. Notice the y coordinate is a decimal that I haven't bothered to figure out yet. So, but apparently, because of the picture, apparently I got it right. Again, it'd be really unlucky if it looks so good, but the more I zoom in, the better it looks. So that really does look like a maximum. That's kind of cool. And of course, there's another minimum. I can see that one exists there. And of course, if I throw in, wasn't it just, I guess I can fix this really quick and just make that an 11. Hey, look, got that one right too. So that's kind of cool.
Did you limit the function so that it's only in that specific spot? Right?
Yeah, and I'll put this in the notes.
Okay.
I'll copy this into the notes. That's how you do it in Desmos, which is kind of nice because it just lets you, you know, not get overwhelmed by things that you see.
Then that's
What's your thoughts on this? Are you tracking? Are you thinking, hey, you're right, this isn't actually terrible?
I'm thinking I can plug equations into Desmos and find all the answers.
Yeah, Desmos is really cool. There's no excuse for getting it wrong and not knowing it. I guess that's the only thing the main thing I want to say. If you get it wrong and you don't know it, you're really screwing up. That should never happen. Awesome. All right, as usual, I'm over a little bit. So you have, this is due Sunday. Feel free to send me any questions you have. One thing I would love to have done is, actually, maybe I'm going to do this just as a parting shot with you. Let me shoot a quick picture of this so I can get it in the notes before we're done. I want to show you something amazing. I think Dominic is in my other class, but I was grading those projects where you guys found slopes of, where you found slope of a implicit equation, and I noticed there weren't any implicit equations in your assignment, so I decided not to include them here. But just take a look at this. This is he found it a really an amazing. I'm going to Desmos on my computer because I have stuff saved. I think it's this one. So check out, I mean, wouldn't this be an interesting one to do, if you will? Because notice it's got, well, there's a max, there's a minimum, there's a max, so there's 3, and then you come down here, minimum, maximum, minimum. So this would have 6 answers to it. And now maybe algebraically, now that you stare at his equation up here, maybe algebraically you say, I don't know if I could solve that algebraically, and the answer to that is probably, you're right, you can't. But this is really cool in the implicit world. And notice in his case, one of the reasons I saved his is, look how crazy this graph is. I mean, I was just so impressed with what a ridiculous discovery this was. Now, how many maximums and minimums does it have? It was like 50 of them. And they just kind of keep growing, but it's like, what a ridiculous, it's like, talk about a cool graph for Halloween. It's like a Halloween graph. But that's a rabbit hole. Does that make sense? Like, find the critical points. Wouldn't you like to have that for a problem? No, thank you. But it's just kind of interesting. Okay, I'm gonna shut up. I'll stay after if you want to ask me project questions in particular, because that's the last chance you're gonna have to ask me project questions since it's due Sunday, and I'll be showing you kind of the efficient way to answer that by the time I see you again on Monday. So feel free to ask me those questions. Otherwise, I'll see you on Monday.
I actually did have a question about the project.
Okay.
So I was kind of looking at your equation and like, you know, your points and stuff and kind of trying to figure out how you did it so I could solve it for mine. And your numbers, I don't know, maybe I'm just spitballing here, but is your number that you multiply out front of your equation and your additional number that you add to the backside, did you find those using your Y values? Is that kind of how you do it? Some form of using them? I think I have an idea of how to do it, but
yeah, you're exactly right. That is what I did.
okay. I think I know how to do it. I don't want to like blurt it out in class. So
Yeah.
for everybody that's still
Well,
trying to
the cool thing is the proof's in the pudding. Like if you come up with an algebraic technique and it works, then you'll be able to see in the graph that it works. Like you type in what you did algebraically and it's like, oh, look at that. It worked. It goes through those points perfectly. Then you'll know you got it right. If it doesn't, then you'll know you didn't. So it kind of checks itself in a sense, which is kind of cool.
All right. That was my only question. I just wanted to make sure I was kind of thinking the right way.
Yeah, sweet.
All right. Thanks, Doug.
Would you do one at a time like that?
What?
Would you do one at a time like that?
I used both of them simultaneously because